Oh, wait. Hi, everyone. So welcome to our very special glue event here today at the CFA, and welcome to everybody who's watching online, too. And so we're trying to take only half an hour to show you the wizardry that is glue, and many of you are going to stay for a tutorial after this short introduction today, and several of you are going to come back tomorrow, and I'm guessing that some of you who didn't sign up for the tutorial are going to want to come back after or tomorrow, so just talk to us afterwards and we'll see if we can make some room. So it's going to be a very short introduction. The story is that my friends and I have been using what's called linked view visualization for a very long time. And we realized that many astronomers actually don't know what that is. Tom is absolutely going to explain that to you. But a long time ago, I was lucky enough that Tom Robitaille, our excellent esteemed speaker today, and Chris Beaumont were both here. Tom was a postdoc and Chris Beaumont was a graduate student at the CFA. And they sat down and wrote the very beginnings of GLUE, which is a little hub that lets data sets be shared without having to merge them in what became this very beautiful Python-based visualization environment. And I don't want to say much more than that, other than that Tom is now essentially the main developer on GLUE and the most expert person around. And so we are extremely honored to have him visiting from England, where he now lives. He just recently departed his small research group at the Max Planck Institute, which he took up after leaving here. So I give you Dr. Tom Robitaille and GLUE.
Thank you. So yeah, the intent of this half-hour, kind of talk / demo is just to give you a kind of taste of what you can do, what GLUE is about first, and maybe how you can use it on various data sets. Hopefully, inspire you to actually want to try it out, and of course, for those of you who then stay on to the tutorial, then you can learn how to use it. So this is meant it's kind of halfway between a talk and a demo. So the idea behind GLUE is, GLUE is a tool for linked and multi-dimensional data exploration, and I'm going to explain a little bit more what we mean by that. Now, there's several problems when we talk about data nowadays. So actually, many of you, I imagine, have dealt with, for example, tables of data. And if you think about tables, actually tables are highly dimensional data objects most of the time, because if you have a table with, let's say, 50 columns, you have a 50-dimensional data set. And we need an efficient way to actually visualize that kind of information. So when people talk about highly dimensional data, it's not just a 4-dimensional cube. Tables are highly dimensional data. The second problem with data is that most of the time we don't have one single nice data file for whatever we're doing and nothing else. Okay, so we have data that comes from a collection of sources. We have multiple files typically. We have catalogs, images. Maybe some of the images and catalogs use different coordinate systems. Actually, most of the time, very frequently they will. So we'll have galactic coordinates, equatorial coordinates, things like that. And then there'll be different conventions. Probably some files will assume some kind of magnitude system. Maybe other files will assume different ones. So we actually spend a lot of our time, making those data sets uniform. And what we really want to do is to have the ability to analyze these interactively, bringing in several different data sets together. And so that's where the term GLUE comes from. The idea is you want to glue together data sets. One other important aspect of that motivated the development of GLUE is that we're actually are often interested only in a subset of the data. So when we actually do these very large surveys, then actually sometimes we're interested in finding very specific kinds of objects, interesting new kinds of objects maybe, and discovering new kind of groups of objects. And so we need ways to kind of drill down into the data and look at specific subsets of the data. Essentially, that's the aim of GLUE, and so I'll show now a little bit of a demo of loading some simple data sets into GLUE, and then I'll move on to show some of the more advanced features. Okay, so I'm going to just demonstrate very quickly the use of GLUE with there's essentially a catalog from Glimpse around the Eagle Nebula, and also I'm going to load up an image. Let's see, so. Which is an 8-micron image taken with Spitzer also. So this is the main interface of Glue. What it contains, so Glue is a graphical user interface program, so it's not just command line. So this is the main interface of Glue. If you think about Glue, this is the main way that you'll interact with it at the moment. On the top left is essentially shows you what kind of data sets you have loaded, and this main area here, which we call essentially the canvas, is where we're going to create data viewers. So the idea is that you can essentially can take one of the data sets, the image data set, you can drag it onto here, and create an image viewer. And so this is just a standard image viewer inside Glue. So let's see. So we can do things that you could do in DS9. So we can modify the stretch. I can control click and adjust the contrast. And then, so but this is just one of the viewers. So we can actually make another view of the same data. So we can make a histogram of the pixel values. So let's see. Yep. So here I have a histogram of the pixel values. So I'm going to adjust the stretch just so it's a little bit easier to see what's going on. Okay, so I'm going to put the x-axis on the log scale. So you can essentially create these data viewers for whatever data you have. So let's say we have this other data set here. This is a catalog. So we can make a scatter plot of two other parameters. So let's see. Okay, so for now, let's just say, okay, so this contains Spitzer and 2 mass information. So you can have, for example, the 3.6 magnitude and the 5.8 magnitude. And then let's say, okay, we want to make, again, another view of this data set, which would be, for example, a histogram. Okay, so we can make a histogram of one of the parameters in the catalog. Okay, so let's select something else. So we can do the JMAD magnitude. So the idea is now that we have these different data viewers. What we want to be able to do is to explore certain regions, certain areas of each data set and see what they look like in other kind of visualizations. So as an example, I can take the image here and I can select essentially, so let's actually zoom into this region up here. So this is the Eagle Nebula, the pillars of creation are here. So I can take this tool here and it allows me to select certain regions. So I can say I'm interested in this region here. When I do this, what will happen is that the selection from that area here will get then propagated to this viewer. Okay, so I can, in here, the problem is that this is only a small fraction of the pixels, so I can renormalize the histogram. What this is saying is the pixels in that region essentially have this distribution compared to the overall distribution of pixels. Okay, this is what's called a linked view. So we can essentially link a selection in one viewer and see what it looks like in another viewer. Another example is in the scatter plot here. I can essentially select some points up here. So I can use there's different kinds of ways of selecting. You can have a lasso selection or rectangular. And then essentially in the bottom right here, so I need to do the same as what I did just now. I can renormalize. And so let's see. So actually many of the points don't have necessarily J-band magnitude, so we can change and put. So I'll do this. And you can see that the points that are selected are predominantly faint in 4.5 micron. Okay, so there's a number of things you can do in this to make the analysis easier. So in this case, you'll notice that, for example, what you really want to do is to actually make a color diagram or color magnitude diagram. But the catalog I was using doesn't have that information. So what we can do is we can actually create new components. So I can say, I'm interested in creating a new component. And then which will be some kind of arithmetic combination of different components in the existing data sets. So, well, in this case, we want to make a color diagram. So I can find the components here I care about, which are the magnitude in 3.6 to 8 microns. And I can build any kind of arithmetic expression that includes these components. So, for example, 3.6 minus 4.5. And I call this. So I'll call the component 3.6 minus 4.5, and I can add it to the catalog dataset. I can then in here use, essentially I can put, for example, on the y-axis, 3.6 minus 4.5. Okay, and then I can go and I'll create just another one for another color. So I can do, right, so I can do 5.8 minus 8.0. Okay, so with this, I can now actually construct a color diagram. So let's see. Okay, so now we see this is actually a standard Spitzer color diagram. And then I can actually select points, for example, in here, and then see what the properties will look like in this panel here. So I can select, let's say, a bunch of points from here. Okay, and so then the points here will then be highlighted in this histogram. Okay, so the selections still propagate in that way. Okay, but what we really want to do, the most important part about glue is we want to essentially be able to use these data sets together. At the moment, I've been showing essentially just doing selections on this side and selections on this side, and they don't really talk. Now, essentially what we can do is we can define links between the data set. So essentially identifying components in each data set that are the same or mean the same thing, or mean something that can be related by some mathematical transformation in order to link the two. So in this case, basically both the catalog and the image have information about coordinates. And in fact, in this case, I think both of the data sets have galactic longitude and latitude. So if I go up here to the link data menu, I can select essentially, I have a data set here, and then I have the other data set here. I can click on, for example, B, and I can say this is the same as latitude, okay? And I can glue these together. And then I can take the same, I can do L and longitude and glue these. Now, in some cases, you might have more complex transformations. And so if that happened, then there's an advanced menu, and you can actually, for example, have more complex coordinate transformations. And as I'll show in a minute, you can also define your own curve transformations. So once we've done this, we can actually take the subset of points that we created. Okay, so it takes a little while, because the image is large, it takes a little while to set up the links, essentially, between the different data sets. Once this is done, what we'll do is we're going to take the subset from the catalog here, and we're going to overplot it on the image and see how what the spatial distribution of points looks like compared to the background. Okay, so this just takes a second. Essentially the mosaic on the left is quite large, and so before it wasn't actually reading the whole data set. To set up the links, it has to do that. Okay, so yeah, okay, so there we go. I can now select the catalog here and overplot it on the image. Okay, so the red points are the same now as what you see here. Now, we can see actually that the points from this diagram here have a spatial distribution that's actually pretty uniform, so that we can actually explore what different selections do. So if I actually now select this region up here, I can see the selection of points is still reasonably uniform. And then, of course, if I go over here, I actually am now selecting things that are red in both 3.6 minus 4.5 and 5.8 minus 8. And so actually this is a standard way of selecting Young-style objects. And so I can actually see intuitively that if I select the objects here, then suddenly the distribution of the sources becomes more clustered. And so, of course, this goes both ways. We can also say, well, actually, now I see this, so we can zoom in a bit. There's several regions here. I can say, well, I'm interested it looks like there's a bunch of sources here and a bunch of sources here. So I can then say, I'm actually going to select this region here. And what this will do is it will select both the pixels in the image and the actual sources that lie in the same region, because we've created this connection. So in this case, let's see, I'm just going to turn off, it's actually selected both pixels from the image, which is why the histogram has updated, and sources from the catalog. So I'm just going to turn off the image layer here. You can see actually that this is just many points that have been selected. Okay. So what I can do is I can actually, if I want, I can make another selection, okay, around here. And then we can actually see how that propagates to other data sets. So if I made sure that the selection up here wasn't selected, sorry, and then now I've actually selected points. So you see these points up here. Actually, what's interesting is that I actually didn't know this before looking at this data set. It looks like the distributions in color space are slightly different for this region and this region. It actually looks like there's more green points up here, whereas there's actually fewer points in this region for the green data set, whereas for the red one, actually there's a high density of points here. So actually what that tells us is this is a region that's probably less evolved than the region in red here. So actually this is a nice way to kind of explore the data interactively. And using the linking between the data sets to really see how, essentially how the young stars, where are the young stars in the region, how can we identify them in color space. Okay. So, the other thing that I should just quickly mention that you can do is when you have a selection like this, you could then say, actually, I only care about things that are to the upper right of this diagram. So I could take a selection, and then I can actually make logical operations between selections. I can say I want to now select a subset of that selection. So I can say I want to go in AND mode, and then essentially draw a shape like this. And what this will do is it will only select red points that are inside that area. Okay, so then it refines the selection. Okay, and then you can actually see the points on the left updating. Okay. So Glue essentially supports many different input formats. You can actually read in, of course, FITS files, HDF files, many different ASCII table formats, and then you things like Excel tables and things like that. And it's also very easy to build your own readers. You can have link selection automatically within datasets, so that's the simple thing where you show, for example, an image and you select the region and it shows the pixels, in the histogram. But you can also link across datasets, and you can have things that aren't one-to-one mapping, which could be through any kind of complex transformation. And then I've also shown how we can define derived components. Glue is written in Python, which basically allows us to so everything that I've shown before can be done through the graphical user interface. Now, people also sometimes want to interact with the data from the command line. You don't have to, but if you want to have more detailed access to the data objects in Glue, then you can do that. So just to give an example here, I can actually I'm going to just close this window here. I'm going to create a terminal inside Glue. So this is just a standard Python terminal inside Glue. And I can do things like access specific data sets. So I can do data equals data collection 0. This accesses the first data set in Glue, which is the catalog in the top left. And then if I access the data, I can access the subsets. And then there's actually 2 subsets in this data. And then for each of them, for example, for the first subset, I can extract, for example, a mask of true and false, which points are selected. And then, of course, you can continue and do any kind of analysis you would have done normally in Python, if you're using Python, for example. So the idea is you can really, and you can also define selections from this terminal. So if you want, you have the option to drop down into Python and interact with any of this from Python. I'm not going to show this now, but it's also possible to launch Glue from Python. So if you have a Python session and you have data objects in it, then you can actually launch Glue from your Python session. And then once you close Glue, you still have access to all these kind of data objects and selections. So you can use it as a step in your workflow. You don't have to use it as your only step in the workflow. Okay. Glue is also meant to be highly customizable. So we've made it so that you can essentially, it's not meant to be a static application. If you want to be able to read different file formats, if you want to define your own data viewers, then that's something you can do. And in fact, we've actually tried to make it as easy as possible to do that without actually understanding how to build a graphical application. Okay, so before working on this project, I actually didn't know how to work on a GUI, and actually, maybe many of you haven't, also done GUI programming before. That's fine, and you should be able to customize things without having to write this kind of code. So just as an example, this is a simple example of how. So you can essentially create these config.py files that you put in the directory where you start Glue. And in that kind of file, you can put Python code that looks something like this. So this actually essentially implements a function that identifies if a file is a JPEG file, and essentially, if so, how to read it. Okay, this is a very simple example, but this will essentially add a JPEG reader to Glue. So after that, if you put this in the file, you'll then be able to read JPEG files. And there's no graphical user interface code or anything here. It's very easy to write. This is another example. So I mentioned that there's these linking functions. So for example, for coordinates. So this is an example of creating a new linking function. If you have some data set that's in degrees and one in radians, and you want to create a link between the two, then you can create a custom linking function that does that this way. And I'll just very briefly show. So it's also possible if you're a bit more dedicated, you want to create a data viewer that you're going to use a lot in different settings, and you want other people to use, you can also develop plugins. So I'll just show a very quick example here of essentially a plugin that I wrote that lives in a separate package. And what you can do with it is essentially import essentially any catalog that you want from Visio. So that's just an example of a plugin. So I wrote a paper a few years ago, which was on young sources, essentially in the Glimpse survey. So if I do this, then I see the catalogs returned by Visio, and I can do, for example, let's see here. I see how many sources are in each catalog, and then I can actually say, I want to import both of these catalogs into Glue. I'll import them, and then they'll appear as datasets in the top left here, once it downloads. Okay, so then I have 2 new datasets here, from which essentially I can create, so I can make a new tab, and then I can actually now create new viewers for this. Okay, so then I have access to all the components and the data. So, for example, RA and DEC, and then you can actually see it's a galactic plane survey. All right. There's more examples I can show you if you're interested. We have actually quite a few examples of plugins we're developing. So if you're interested in finding out more, I'd be very happy to show. But essentially, to move on, I just want to spend some time talking about some of the things we're thinking about. And especially one thing that we're working on currently is to implement 3D viewers in Glue. So I'll give a demo of that just to give you an idea of where we're at. We also are thinking about tools for doing spectroscopical analysis. So, for example, if you have a data cube, and you can already do some of these things in a simple way, but you can extract regions of a data cube, a spectral cube, and then you could actually go and then fit the lines with whatever model you want. We also want to make it easier to use Glue from the Jupyter Notebook, so also formerly called the IPython Notebook. Again, if you're interested in seeing what we can do currently with that, I can show a little bit in the tutorials. And then we also want to make sure that it works with very large data sets. So I'm going to just spend the rest of the time showing you what we've done in terms of 3D. I should say that this is not just me, so Penny Kian, who's here, also basically actually wrote a lot of the code that's gone into the 3D viewers. Okay, so let me just start a new session. Okay, so I've picked there's different data sets we can use for that. I've actually picked a data set which is a Chandra event file, and that I used to use a different file for demos, but a couple of weeks ago I was at a workshop where someone said, can we use event files? And it turns out I thought the answer was yes, opened it, it didn't work. So now it's fixed and you can use event files in Glue. And so I'll show an example of this. So event files are nice because essentially they'll give you the, for example, the position of photons in 2 dimensions plus other quantities. So it's actually a very good use case for 3-dimensional viewing. Okay, so one of the viewers that we have is a 3D scatter plot. So we can do what I did originally was I would show the, essentially this is the position on the chip. There's actually multiple chips, and so it overlaps everything. But I did chip X, chip Y, and then here I can show, for example, energy. Okay, so this is a view of an event file where essentially it's actually there's essentially spectra in here, and I'm sure there's people in the room who know more about this than me. But this, so essentially this is essentially the position on the chip, and then the vertical axis here is the energy. Okay, so it turns out that actually this is. I was talking to an X-ray expert yesterday. This is not really how you would view it. You would look actually at X and Y, and then. Okay, so what we see now is the source is in the center here, and what these things are essentially the spectra of that source in different orders. So each of these lines here corresponds to a different order. So I can now, in this 3D viewer, I can color code points by certain quantities. So for example, I could, color code it by energy, which essentially would duplicate the information in terms of the Z direction, so it's the same quantity that's being used for that. But I can also use other things. So, for example, there's this TGM variable, which is related to the order of the spectrum. And many points here are actually now too dark. These are points where the order was set to 99, which is because it couldn't figure out which order each photon was in. So let's see. I can change this to -5 to 5. And so essentially each of these different lines here has a slightly different color. That's because essentially each line is a different order in the spectrum. And you can really, it's really nice to be able to kind of interactively explore this. You can then do things like essentially make other viewers where we can show that same TGM quantity. And then I'll again go from, let's see, -5 to 5. Okay, so each of these peaks in the histogram corresponds to a different order. I can now make selections in that plot, okay, and then see the selections propagate to the 3D view. So essentially here I've selected all of the things that had an order of -1, and then I can make another selection here where I select all the ones which have an order of 1. I can also select, essentially this is the order of -4. You can really see all of the photons being highlighted here. Okay, and in the center this is just the 0th order. So that's just an example of using 3D scatterplot to visualize the data and essentially having selections that are linked, that are propagated there. This is something that we're actually working currently on implementing selection in the 3D view. So there's different ways you can do that, but we have some already preliminary implementation of that. So you essentially can make selections of points from different angles and then essentially constrain a region in 3 dimensions. Okay, so another example of a 3D viewer that we've implemented is, let me just close this, is a volume rendering viewer. So if the scatter plot viewer is good if you have things like event files, if you have catalogs that you want to view in 3D that have many dimensions, many columns. So another kind of viewer that's useful is if you have more like a gridded data set. So this could be a radio data cube or something like this. So this is what I'm going to show is a CO cube. So let's see. Okay, so I'm just going to change the color. Okay, so what this is it's a spectral cube. This is the position plane, and then vertically we have the spectral information. I can actually, to make it look a little bit more sensible, I can actually squeeze the spectral axis a little, and then I can see essentially this is our CO cloud. Again, I can actually make selections in other views. So, for example, I can make a histogram of the pixel values. Okay, and then I can also make a dendrogram, which is a tree representation of the structure of the cloud. So, let's see. Okay, so this is a dendrogram of the cloud. So each of these vertical lines corresponds to a structure that's essentially contains a peak in the emission. And these structures are then linked together as you move down and down in intensity levels. Okay, so the y-axis here is the intensity. The x-axis actually doesn't mean anything. It's just we have to show the tree somehow. Okay, so the idea is now we can go and make selections. For example, we can make a selection in the dendrogram, and so see that selection highlighted in 3 dimensions. So then you can actually link, you have a better idea of, with this kind of diagram, it's often very difficult to figure out what this means. So we know, for example, okay, there are 4 structures here that are merged into one, and then there's 2 other ones, but it's very hard to conceptually understand what this corresponds to. So I can then, for example, make another selection of a different structure in the cloud, and then see this be highlighted down here. Okay, and so as I turn around, I can visualize in 3 dimensions what this structure looks like. Of course, we can also make selections, for example, in a histogram, and see which structures in the tree it overlaps with, and then also see that being highlighted in the data. Okay, so we're currently working also on implementing selection for this kind of volume rendering. Okay, the other thing I'll just quickly mention is there's also a lot of other tools that are in Glue, and we can build a lot more of these tools as plugins. So for example, so I'm just going to close the histogram here and make an image view. So this is now a more traditional view of a cube, which is just essentially looking at slices, and I can go through the slices and again see the selections. And so what we can do is there's several tools that are built in. For example, you can take a slice of this cube along an arbitrary path and see the position velocity diagram. So let me make this smaller. I'll just move this over here. Okay, so essentially this is a position velocity diagram along this arbitrary path here. And then you can also do things like extracting. I mentioned before, you can extract essentially simple spectra of regions. I'm not sure where the window went. So, yeah, okay, so it's behind there. Sorry. So let's see. Okay, so then once you have this, then you can actually do things like fitting spectral lines. So we're working on having more advanced functionality there. All right, so the Glue is actually very easy to install. We've actually managed to get it included by default now in the Anaconda Python distribution. So if you use Anaconda to manage your Python distribution, you can access it by default there. And then, I've also recently put a lot of work into rewriting a lot of the documentation on the website and explaining a little bit more how you can build custom tools that work in Glue, or how to use Glue in the first place. And also, if you're interested in getting involved in development, there's now information to help with that. And all the code is on GitHub, and so it's all freely available. If you are interested in contributing to Glue, then you can come and speak to either Alyssa, myself, or any of the other people involved in Glue. But yeah, I think I'll stop there and then encourage you to come to the tutorials. Thank you.